Hi my dear friends, welcome back to our YouTube channel. This is your ADC Max. In this class, we are going to describe or list out the properties of eigenvalues and eigenvectors. The properties of eigenvalues and eigenvectors. The first property is the sum of the eigenvalues is equal to the sum of the leading diagonal elements. This is often called as trace of the matrix. So first property, the sum of the eigenvalues is equal to the sum of the leading diagonal elements is often called as trace of the matrix. Is that right? Second property, product of the eigenvalues. Product of the eigenvalues is determinant value. Is its determinant value. Right? So sum means sum of the leading diagonal elements. Product means its determinant value. Third one, a square matrix A and its transpose have the same eigenvalue. What is the transpose of the matrix? Transpose of the matrix is nothing but if the A transpose of the matrix is nothing but we can change the rows as columns. We can change the rows as columns. So the matrix A and its transpose have the same eigenvalues. Right? Right, sir. Because anyhow when you change the rows as columns, diagonals cannot be changed, isn't it? Diagonals cannot be changed. So that's why we will get the same eigenvalue. Fourth one, the eigenvalues of a triangular matrix are the leading diagonals of the matrix. What is my triangular matrices? Please kindly go and watch our separate video, types of matrices. Triangular matrices, there are two types. One is upper triangular matrix, for example, A, B, C, 0, D, E, 0, 0, F. So if you fix the diagonal, then the triangular is formed above the diagonal element. This is called the upper triangular matrix. And once again, this is another example. It is A 0 0, B C 0, D E F. So when you take this diagonal element, then when we construct a triangle below the leading diagonal elements, that is called the lower triangular matrix. So these are the two different types of matrices, triangular matrices. Upper triangular and lower triangular. So once when we have such triangular matrices, then the eigenvalues of the triangular matrix are the leading diagonal elements. So that is the concept. And the fifth one, the eigenvalues of a real symmetric matrix. When we say that the matrix is symmetric, A transpose equal to A. The transpose of the matrix is equal to the A, then it's called the symmetric matrix. Symmetric means, as you told you that the leading diagonal is fixed, so we'll get the mirror reflection. So that's why the real symmetric matrix means the eigenvalues are real numbers only. What about the eigenvalues of the unit matrix? Unit matrix is often called as identity matrix. I. What is the I? Suppose I equal to 1 0 0 0 1 0 0 0 1 is a 3 by 3 matrix. What about the leading diagonals? It is 1 only. So that's why the eigenvalues of an unit matrix or identity matrix are nothing but unity, 1 only. Right? Because 1 in the beginner. And an eigenvector cannot correspond to two different eigenvalues. So let us see that. Suppose when we have lambda 1, lambda 2, lambda 3, three eigenvalues for 3 by 3 matrix, then we get the corresponding the eigenvectors x1, x2, x3. Is right? Now the reverse is not possible. What's the reverse? An eigenvector cannot correspond to two different. For example, this is the eigenvector of lambda 1. This is the eigenvector of x2. This is for the x3. But what's the reverse? What's the reverse? Even though, for example, this lambda 1 may have more than one eigenvector. It may generate more than one eigenvector once the system of equations is identical. We assume that x1 0, x2 0, x3 0. It will generate more than one eigenvector. But the reverse is not possible. What's the reverse? Suppose this is the eigenvector, it cannot be corresponding to two different eigenvalues. The reverse is not possible. The reverse is not possible. Right? Then the eighth property is if lambda is an eigenvalue of an orthogonal matrix. When we say that the matrix is orthogonal, let us see that separate video I made for orthogonal matrix and their properties and examples. Let us go and watch. Now here, when we say that the matrix is orthogonal, the matrix is said to be orthogonal A transpose equal to A transpose A equal to I. Let us see that a matrix A is said to be orthogonal if A transpose equal to A transpose A equal to I. Got it? Then what about the 1 by lambda? 1 by lambda is also an eigenvalue of the orthogonal matrix. So lambda is an eigenvalue means its inverse is also an eigenvalue. Why? Because the reason was already we know that A inverse is equal to A inverse A is equal to I. Is right? Already we know this result. But by the definition of an orthogonal matrix, A transpose equal to A transpose A equal to I. Now by combining these two, what happened? If A is an orthogonal matrix, then what we say that the A transpose and the A inverse are same. A transpose and the A inverse are same. Isn't it? Now what says this property number 3? A square matrix A and its transpose have the same eigenvalues. So once if A is an orthogonal matrix, what about the A transpose? A transpose is also have the same eigenvalue. So lambda is an eigenvalue of A. So lambda is an eigenvalue of A transpose because of by the property number 3. Now by the definition, A transpose equal to A inverse. So that means that 1 by lambda is an eigenvalue for A transpose equal to A inverse. So it's nothing but 1 by lambda is an eigenvalue of the same orthogonal matrix. Understand? The last property, the ninth property is the eigenvector corresponds to distinct eigenvalues of a real symmetric matrix are orthogonal. So the two distinct eigenvectors of the real symmetric matrix are orthogonal. When we say that the matrix is orthogonal, that is A transpose equal to A transpose A equal to I. Now when we say that the two vectors are orthogonal vectors, go and watch the separate video I made for orthogonal vectors, pairwise orthogonal vectors, orthogonal matrices example. Please go and watch it. Now here, when we say that the two eigenvectors are orthogonal, very simple, the product of these two is equal to 0. Either x1 transpose x2 0 or x1 into x2 transpose is 0. Once it satisfies any one of these equations, then we say that both the eigenvectors are orthogonal to each other. So this is the ninth property. The property says that the eigenvector correspond to two distinct eigenvalues of a real symmetric matrix are orthogonal. The 10th property is if lambda 1, lambda 2, lambda 3, etc., lambda n be the eigenvalues of a square matrix A is of order n cross n. If is of order n cross n rows, n columns. Suppose when we have 2 rows, 2 columns, we get 2 eigenvalues lambda 1, lambda 2. Suppose when we have 3 rows, 3 columns, then we get 3 eigenvalues lambda 1, lambda 2, lambda 3. So in generally, if it is of n cross n matrix, n rows and n columns, we get the n eigenvalues, namely lambda 1, lambda 2, lambda 3, etc., lambda n. Now, what are the eigenvalues of A inverse? It's nothing but the inverse of the eigenvalues. So 1 by lambda 1, 1 by lambda 2, 1 by lambda 3, etc., 1 by lambda inverse. What about the powers of eigenvalues A power n? What are the eigenvalues of A power n? N is a positive integer. Then we can make the powers. Lambda 1 power n, lambda 2 power n, lambda 3 power n, etc., lambda n power n. Suppose n equal to 2. What are the eigenvalues of A squared? It's nothing but lambda 1 squared, lambda 2 squared, lambda 3 squared, etc., Right? What about the k? K is a scalar. Then when we multiply the scale of the matrix A, we get Ka. What are the eigenvalues of Ka? Then multiply the same scalar with the eigenvalues, each eigenvalues. So k lambda 1, k lambda 2, k lambda 3, etc., k lambda n. What about the A plus or minus C into I? C is the constant or specific value or maybe the scalar value. So C into I. What is the I? I is the identity matrix. Then the eigenvalues of A plus or minus C I is nothing but the same thing. I means it is 1. Understand? Identity matrix is 1. So C into 1, C. So add or subtract with the lambda 1. Lambda 1 plus or minus C, lambda 2 plus or minus C, lambda 3 plus or minus C, etc., lambda n plus or minus C. And the last one, this is very interesting. What are the eigenvalues of adjoint of A? Very, very interesting. The adjoint of A. How will you get the adjoint of A? The transpose of the cofactors of the matrix. Transpose of the cofactors of the matrix. Now, we can get this adjoint of A from the definition. The inverse A inverse equal to 1 by A transpose into adjoint of A. What is the transpose of A? It's named a number. It's a scalar quantity. Is right? Now, let us fix the adjoint of A. Let us cross multiply to this side to get determinant of A into A inverse. What are the eigenvalues of A inverse? 1 by lambda 1, 1 by lambda 2, 1 by lambda 3. Right? What is determinant of A? It's nothing but the product of the eigenvalues, or otherwise it's a number. It's a scalar. It's a constant value. So let us multiply the determinant of A with the inverse of the matrix. So by the property, the first property, we get this way: determinant of A into 1 by lambda 1, determinant of A into 1 by lambda 2, etc., etc. Determinant of A into 1 by lambda n are the eigenvalues of the adjoint of A matrix. What is determinant of A? Is nothing but a constant. So it looks like a scalar multiplication. But the inverse, why get the inverse? By using this idea. A inverse is equal to 1 by determinant of A into adjoint of A. So by this way we will get the adjoint of A equal to determinant of A into A inverse. So this is the concept. So these are the properties of eigenvalues and eigenvectors. I hope everyone understand and enjoyed this topic, properties of eigenvalues and eigenvectors. Please kindly subscribe and share and comments our YouTube channel ADC Max. Thank you. Thank you so much for watching our YouTube channel. Thank you, sir. Thank you.